Hello Internet, it's Jonathan. Welcome back to Jenkins Robotics. Over the past few weeks, I've been working hard on my first grad school level robotics project. I was tasked to design, fabricate, and build a tactile sensor for humanoid robotic applications. So in this video, I'm going to take you what I've been doing in the last few weeks. Let's get started. I work in the field of industrial robotics. I design, manufacture, and integrate industrial robots into the manufacturing line. Industrial robots are great at performing the same task repeatedly. Teach them what you want them to do, and they will keep doing it, such as unloading parts from a machine and loading new parts into that same machine. These environments are referred to as structured environments, where the robotic interacts with relatively consistent variables. Humanoid robots takes this to the next level. They are designed to operate in unstructured environments, where variables are constantly changing. Compared to industrial robots, humanoid robots have improved dexterity, locomotion, sensory feedback, and intelligence. Today we're going to be talking about sensory feedback. Humans have 5 sensors: vision, smell, taste, sound, and touch. Touch specifically is very important for object manipulation. Sensors designed to give robots the similar sensation of touch are called tactile sensors. These come in a variety of shapes and sizes. Many tactile sensors operate on different principles on how they convert physical stimuli to electrical signals. This is called transduction method. Some of the most common transduction methods used are resistive, which measures the change of an object's electrical resistance; conductive, which measures the change of an object's electrical conductivity; inductive, which measures the change of electric fields or magnetic fields; and optical, which measures the change of light using cameras or optics. There's far more types of transduction methods used in tactile sensors. Each comes with their own pros and cons. No matter what type of sensor you decide, all tactile sensors need to meet 6 general requirements. First is selectivity, which means being able to detect the desired stimulus. Second is reproducibility, being able to generate an identical response when the same stimulus is repeated. Third is stability. This is the ability to have a precise, constant reading of the with minimum noise or drift. Fourth is sensitivity, which represents the minimum amount of stimuli that can be detected. Fifth is cost. If the sensor is too expensive, it will not be economic to use. And lastly is size. If the space required for the sensor is too large for the application, then it simply cannot be used. So, with that general information, I was tasked to create my own tactile sensor for the use of humanoid robotic fingers. This custom sensor needs to meet some additional requirements on top of the general requirements. First is size. I'm aiming to create a tactile sensor similar to the human thumb. So I do not want to be too much larger or smaller than a human thumb. The second requirement is the type of measurements I'm trying to conduct. First, I would like to measure the amount of force my robot exerts on an object. Second, I would like to measure the temperature of that said object it's interacting with. So I want to measure force and temperature. The third requirement, I want to use 3 different sensors to perform the task. 2 specifically to measure the force, and 1 to measure the temperature. Lastly, what's the point of creating a sensor without using the data? So I want to make a simple haptic feedback device that will communicate to the user the amount of force and temperature that the sensor is reading in a visual way. So, with the scope of the project laid out, it's now time to start the designing. After careful consideration, I decided on the types of sensors I want to use. First is a thermistor. A thermistor is a resistor that changes its resistance with the change of temperature. They are small, cheap, and accurate enough for this application. Second is a force-sensitive resistor, or FSR for short. Force-sensing resistors are robust pressure sensors that generates a change of electrical voltage when an external pressure is applied on them. FSRs are made using two electrodes separated by a compliant conductive medium. When external force acts on the sensor, it deforms the conductive material. The deformation causes a change of distance between the two electrodes, causing a change of resistance across them. This can be measured by measuring the change of voltage. So FSRs are good at measuring a large pressure change. So we will also want to balance it out with something that can measure very light forces. To do this, I will use a Hall effect sensor. They are a type of inductive tactile sensor that measures the change of voltage created when two magnetic fields interact. These sensors use a small permanent magnet held above a Hall effect sensor, suspended in a compliant medium. When external force is applied, the distance between the magnet and the sensor changes. Like FSRs, the deformation causes a change in the magnetic field, which also causes a change of resistance in the sensor that could be measured by seeing the change of voltage. Unlike FSRs, the resistance change is quite linear in a Hall effect sensor, allowing you to tune the sensor to the desired range of your application. So we'll use our FSR for larger loads, and we'll use the Hall effect sensor for the lighter loads. With the sensors chosen, I now jump to Fusion 360 to design the finger. We're going to begin by testing each component individually first, wiring the FSR, the Hall effect sensor, and the thermistor independently to the nano. I can test the code and identify the method of wiring for each device and how they should be wired together. Now that each device has been tested, it's now time to design the full wire diagram. This will identify the exact pins that the combined unit will be using. The tactile sensor will consist of two key components: a movable plate and a fixed body. The movable plate will first hold the thermistor nearest to the face of the finger. Below the thermistor will be the FSR. Both the FSR and the thermistor will be embedded into a foam material. This will allow nice even distribution of the pressure when interacting with objects. This plate will also house the magnet that the Hall effect sensor will be measuring. The Hall effect sensor will be located on the second part of the tactile sensor, the rigid body. Using springs, the top plate and Hall effect sensor will move independently from each other. Pins will be used to hold the two components together on slots, prevent them from pulling away from each other. Now, with the design completed, let's go ahead and send off the design to my 3D printers for manufacturing. Now it's time to assemble the components. Assembling the machine took a few days. With that completed, it's time to move back onto the computer and upload the updated code and calibrate the system. We're going to calibrate the system using known weights as references, placing them onto the sensor, seeing their responses, and updating the information used in the code. Now that the calibration is done, we can now demonstrate the use of the sensor. This is my final version of the tactile sensor. On the left-hand side is the haptic and sensory feedback device. On the right-hand side is the tactile sensor. So let's talk about exactly how this works. There's two strips of LEDs on the feedback device. This strips of LEDs informs the user the magnitude of force that the sensor is reading. On the left-hand side represents the magnitude of force measured by the FSR, and on the right-hand side it represents the magnitude of force measured by the Hall effect sensor. Using some sensor fusion, the average is calculated depending on the range of force it's reading, and a numerical value is placed on this LCD screen. A numerical value of the temperature is also indicated on this LCD screen. The temperature also influences the color of the LED matrix. Blue represents any temperatures below 80 degrees Fahrenheit. Green would be any temperatures between 80 degrees and 90 degrees. And red would be any temperature above 90 degrees. So that is my haptic and sensory feedback device. This is a tactile sensor. When pressure is applied on this face, the sensor represents the force and informs the haptic device the measurement that it's reading. As you can see, I'm using about slightly more than half of my range available on my FSR, and I'm using more than 80% of the range available for my Hall effect sensor. The average sensor is currently picking up would be roughly 572 grams. So let's go ahead and test this sensor with some known weights. Using my scale, we're gonna test the accuracy and repeatability of the sensor using some known weights. So, using measuring tape, we're detecting about 330 grams of weight. Placing this on the tactile sensor, we're picking up about 350 grams of weight. As you can see, there's some noise to the reading, but it's roughly between 340 and 350. Going slightly lighter, I'm gonna measure 136 grams of weight using this pliers, placing this onto the finger. Using my tactile sensor, it's measuring about 102 grams of force. This tactile sensor becomes less accurate the lower the weight is. So now I'm gonna go ahead and calibrate with my lightest object, 40 grams of weight. The lightest it can pick up is roughly 40 grams of weight. It's measuring about 51 grams. I'm going to go ahead and try to detect 629 grams of force. Placing this onto the sensor. It is measuring 663 grams of force. So we're going to go ahead and measure the temperature sensor compared to my infrared thermometer. So pointing to the face of the gripper, I'm measuring 80 degrees Fahrenheit, 79 degrees Fahrenheit. And the temperature sensor is also reading right on the edge of 79 and 80 degrees Fahrenheit. It takes some time for the heat to transfer into the gripper. Once it does heat up and goes over 80 degrees Fahrenheit, it then changes green. To speed up the heating process, I'm going to use my heater and heat up the surface. Let's heat it up past 90 degrees. Alright, heating it past 90 degrees, using my thermistor, I'm measuring roughly 98.9 degrees. Try and hold that again. I'm measuring roughly 96.5 degrees. The temperature sensor is reading 94 degrees Fahrenheit. And when force is fully applied onto the sensor, it updates the light colors, and it is now red, being over 90 degrees. So that is my tactile sensor with both temperature and force measurement. So now that the sensor is completed and we've measured and analyzed the data, let's talk about how well this sensor actually works. So let's begin by reviewing the haptic feedback. The haptic feedback unit does display pretty accurate information what it gets from the sensor. It does basic fusion analysis of the two types of force readings that it's picking up to do an average depending on the amount of mass it's detecting. For low weight, where the FSR is not picking anything up, it relies more on the Hall effect sensor. For the higher weights, where the Hall effect sensor is less accurate, it relies more on the FSR. During that middle ground, when both sensors are producing relatively consistent data points, it does an average between both of them. And the adjustment of the temperature to the color indication of the feedback device is pretty nice. So overall, the feedback device seems to be working pretty well, but that's not the primary focus. The tactile sensor is. So the tactile sensor review is that it is not very accurate for very low end weights. There's a minimum amount of force that I can really pick up, and the lowest I can get it down to is about 40 grams. Anything less than that, it simply just doesn't pick up. Between 40 and 200 grams, there's a lot of noise in it. Above 200 grams, the sensor is more reliable, and it can be relatively accurate all the way up to 1,000 grams, which is what I have it capped up to. Overall, there's a lot of improvement that can be done to improve the sensor. Trying to reduce the size even more while adding more tactile resolution will be very important for future applications. So overall, the sensor works, but not as accurately or with as high a resolution that I wanted it to work. But this is just the beginning. We have two other projects for this class. The next project is designing a robotic gripper. After that, I'll be designing a robotic arm. We're gonna build upon this sensor to be used in those future projects, as well as making a version of this sensor that's more accurate. So stay tuned and like and subscribe. See you next time.